Light quality is something we don't often think about, but if you're into lighting design, photography, or setting up an illegal grow room in your basement, then having a spectrometer to accurately measure light can make a huge difference. The only problem is that most spectrometers designed for these tasks cost well over $1,000. Building a webcam-based spectrometer seems like an obvious alternative. They're affordable and can have a resolution of just a few nanometers. But they've got one major drawback that makes them almost useless for my application. They don't provide data in absolute units. That's when I came across a USB spectrometer from a relatively unknown Chinese manufacturer called Torchbearer. Or is it Arsonist? Or maybe Fire Stealer? Their website can't seem to decide. Priced at under $150, it claims a measurement range of 340 to 1000 nanometers, a resolution of 7 nanometers, and an accuracy of 1 nanometer. But most importantly for me, it returns data in absolute units, with an advertised illumination accuracy of just 4%. It's available on Amazon, but unfortunately, they don't ship to Australia. So I took a chance and ordered from AliExpress, where their store name looks like it was inspired by their Wi-Fi password. With a total of 4 sales and 0% positive feedback, what could possibly go wrong? The seller took almost a week to ship my order, but to my surprise, it arrived via UPS, an unexpected luxury considering AliExpress typically relies on continental drift as their delivery method. The packaging was minimal to say the least, with just a thin layer of shrink wrap surrounding the product box. By some miracle, it arrived without too much damage. Inside the box was a warranty card, the spectrometer itself, a mini USB cable with a suspiciously large connector, and a USB Type-C to A adapter. There was just one problem. This wasn't the model I ordered. When I reached out to the seller, they explained they'd temporarily stocked another model due to high demand over the holiday season, then stopped responding to my messages. As far as I can tell, the only difference between this and the model I ordered is the size and weight, and both should have identical features. The spectrometer is extremely compact and features a mini USB port for communication. Strangely, it doesn't use the USB protocol. Instead, the included cable contains a built-in CH340 USB to serial converter. Plugging the cable into a computer enumerates as a serial port, even without the other end being connected to anything. This means that other cables won't work and could potentially damage the spectrometer. Likewise, the included cable shouldn't be used for any other devices. The Windows-based software is available on Torchbearer's website, but it comes with some significant limitations. For starters, the window size is fixed, making it completely unusable on devices with small screens. You know, the sort of device that you might want to use a mini spectrometer with. It insists on starting in Chinese, but at least it's easy to switch languages. There isn't a lot of functionality either. Only a basic spectrum view and a handful of parameters are visible. Despite advertising CSV exporting on their store page, the only available export format is PDF. Frustratingly, CSV export, along with many other features, do exist within the software, but are disabled for their lower cost spectrometers. The Android app, available on Torchbearer's website and the Google Play Store, suffers from the same limitations. Most of the features shown in the marketing images are missing, and like the PC software, the only available visualizations are the spectral distribution and CIE 1931 diagram. Data export is even more limited. This time, not even PDFs can be saved, and attempting to export data results in an error message. I thought about returning it, but where's the fun in that? Instead, let's have a poke around and see if we can unlock some extra functionality. The serial protocol seemed like a good place to start. Thankfully, Torchbearer provides protocol documentation for some of their other models. While my model had several differences, it was close enough to put together a simple Python library and extract some data. The data samples are limited to 16 bits, despite the advertised 20-bit dynamic range. Maybe Chinese bits are just more efficient. Unfortunately, the bad news doesn't stop there, as the spectrum data appears to be encrypted. With no clear way to decrypt the data, the Android app seemed like the next logical place to investigate. The app is built with the Uni-App framework, which allows cross-platform development in JavaScript with a Vue-based user interface. While Uni-App seems to be extremely popular in China, it's virtually unknown outside the country and has almost no English information or documentation. I used APK tool to disassemble the app, then modified it to redirect console output to a web server running on my computer. This allows me to view the debug messages and gain some insight into how the app functions. When the spectrometer is connected, the model number is used to determine which features should be enabled. We can add features to this list, but we have to be careful, as some features require additional hardware or software to work correctly. For example, flicker detection likely relies on a separate sensor, which is not included in their budget models. Attempting to enable this feature causes the spectrometer to lock up and stop responding to commands. Enabling extra features makes them visible in the app, but many don't work correctly, as the app verifies the model number in multiple places. Finding and bypassing these extra checks lets the additional features work as intended. Unlocking these features revealed some interesting design choices in the app's colour space diagrams. The CIE 1931 diagram is almost passable, at least the colours are roughly where they should be. The saturation has been cranked up to 11, and there's a strange white dot hanging out in the corner. The CIE 1960 diagram's white point has gone for a bit of a walk, but that's nothing compared to the CIE 1976 diagram, where the white point is placed in the bottom right instead of the top left, which means, according to this diagram, the sun should appear lime green. I've reached out to NASA for comment, but so far, I haven't got a response. If you're curious what dropping acid at a lighting convention would be like, here's a simulation of how an incandescent globe would appear according to these diagrams. I created some new diagrams and added them to the app. The Planckian locus looks like it was drawn by a drunk intern during an earthquake, so I calculated the correct coordinates and included them in the app too. With the app improvements complete, 3 additional modes became available: comparative, reflection, and transmission. But I'm going to focus on the standard mode, or we'll be here all week. After selecting a mode, you can choose between single or continuous measurements. When taking a single measurement, the spectrometer continues to send data until the stop button is pressed, even though the data is not displayed. This can interfere with other functions, so I find it helpful to press the stop button after taking a measurement. Manual exposure is useful for dim or rapidly changing light sources, but it has a significant drawback. There's no clear indication of overexposure. When overexposed, the data doesn't appear obviously clipped and can easily be mistaken for real measurements. Overexposure looks similar to the inverse of a typical CMOS sensor response graph, likely due to how the device applies its calibration data. Thankfully, automatic exposure works well enough in most situations. Once a measurement has been taken, the spectrum can be viewed directly, or the data can be visualized in a variety of ways, including several CIE color spaces and color quality measurements such as color rendering index and a range of TM30 visualizations. There's also a color vector graphic, which I believe is Torchbearer's interpretation of a TM30 color vector graphic, but it appears that Torchbearer forgot how to draw a circle when designing it. Various calculated parameters are displayed in the lower section. The Like tab allows you to select 6 parameters to be displayed together, while the other tabs contain lists of parameters that are grouped by category. There's over 60 parameters, and honestly, I have no idea what most of them do. To export data, you first have to save a measurement. Once saved, you can tap the Share button to export as a CSV, PDF, or copy it to the clipboard. Now, let's see how the spectrometer performs under various conditions. I'll also try to verify some of its advertised specifications. I've used external lighting for most of these tests because, as it turns out, you need light to see things. In those cases, I capture the measurements separately to make sure they're not affected. When measuring sunlight, the spectrometer can detect many of the Fraunhofer lines, which are caused by gases in the Sun and Earth's atmosphere absorbing certain wavelengths. The measured spectrum closely matches published solar measurements, except in the ultraviolet range, where the intensity drops off at around 360 nanometers, suggesting the spectrometer might not reach as far into the ultraviolet as advertised. These flesh-burning death lamps are germicidal mercury vapor tubes that primarily emit in the UVC region, well below what this spectrometer can measure. The little cancer tubes are made from fused silica, as regular glass blocks most ultraviolet wavelengths. While we can't see Mercury's UVC emissions, its UVA and visible peaks are easily measured, and all within 1 nanometer of their published values. There are also a significant number of peaks in the infrared region, which don't correspond to any of Mercury's emissions. These closely resemble the spectral lines of argon, which is often included to help start the tube. Fluorescent lamps are another type of mercury vapor tube, but include a phosphor to convert the UV emissions into visible light. As expected, Mercury's UVA peak is absent, while its other emission lines are clearly visible. This black light is similar to a regular compact fluorescent lamp, but instead of a visible phosphor, it has a phosphor that emits in the UVA region. It's built from Wood's glass, which blocks most visible light, allowing only ultraviolet and infrared to pass through. Once again, we can see some of argon's spectral lines in the infrared region. This 650 nanometer red laser diode is currently operating just below its threshold current, behaving like an LED with a spectral width of 18 nanometers. Increasing the current to above its lasing threshold dramatically increases the output, so I'm bouncing it off a matte surface to limit the amount of light reaching the spectrometer. The spectral width has narrowed to 7 nanometers, showing that the spectrometer's resolution at this wavelength meets or exceeds its specifications. This is a great use of the app's comparative mode. I noticed an unexpected infrared peak at 936 nanometers while recording video with my phone. It turns out the spectrometer was detecting my phone's autofocus laser. Like the red laser, it has a spectral width of 7 nanometers. LEDs are relatively monochromatic and typically have a spectral width of around 20 nanometers. This UV LED emits at 399 nanometers. Despite being in the ultraviolet region, this wavelength is still easily visible to the human eye. Next up, we've got a 456 nanometer blue LED. While it emits a significant amount of light, it appears quite dim due to the eye's low sensitivity at this wavelength. This 515 nanometer green LED outputs less than half the power of the blue LED, but it appears significantly brighter due to the eye's much higher response to green wavelengths. Now, this 593 nanometer LED was advertised as yellow, but to my eye, it looks closer to orange. Like most yellow LEDs, it's horribly inefficient, producing less than a tenth of the blue LED's output while consuming a similar input power. A 631 nanometer red LED looks quite red on camera, but in person, it's more of a deep orange. Here's a devilish 666 nanometer LED, which looks similar to the previous LED on camera, but is significantly more saturated in person. Invisible both to the human eye and the camera, but clearly detectable by the spectrometer, this 940 nanometer infrared LED is commonly used in remote controls. Up next is a cheap and nasty white LED, which consists of a blue diode coated with a yellow phosphor. Like a lot of cheap white LEDs, the blue output is significantly stronger than the phosphor, resulting in a very cool output color. There are two common ways of producing purple light with LEDs. One approach is to use both red and blue diodes in combination, which is how RGB LEDs create purple. The other method is used in this LED strip, where a blue diode is coated with a red phosphor. I'm using a 12-volt halogen bulb as a black body source. This bulb advertises a UV filter, which might affect the measurements. I'm increasing the voltage in 1 volt increments every 2 seconds, up to a maximum of 20 volts. I've used the manual exposure mode on the spectrometer, as auto exposure struggles with the rapidly changing brightness. This caused some visible noise at lower brightness levels. Similar to the sunlight measurements, the UV drops off below about 360 nanometers, though it's not clear if this is caused by the spectrometer or by the bulb's UV filter. While I haven't been able to verify all the spectrometer specifications, the measurements I took closely match the expected values, with the notable exception of UV wavelengths below around 360 nanometers. Another aspect to test is the algorithms used to calculate various parameters. For that, I'm going to use the excellent color package in Python, which offers a great implementation of many color science algorithms. Examining sunlight, the calculated parameters are virtually identical. This consistency extends to other white light sources, with both the compact fluorescent and halogen lamp showing less than a 1% difference in the parameters I tested. The white LED shows a difference in color temperature. The LED's output is close to the point of infinite temperature, which isn't well handled by most algorithms. Similarly, purple and blue LEDs also show color temperature differences, but this is expected as the algorithms aren't designed for these light sources. Interestingly, FlameEye shows a color rendering index of over 80 for a monochromatic red laser. But to be fair, we shouldn't blame the tool if we're stupid enough to measure the CRI of a laser. It feels like we've got some unfinished business, so let's take a closer look at the serial protocol and see if we can work out how to decrypt it. Examining the raw data, it appears to use an XOR cipher with two keys, one for the first half of the data and another for the second half. These keys seem to change with every measurement. While it's sometimes possible to calculate XOR keys by exploiting patterns within the data, if we're going to do this properly, we'll need to understand how the keys are generated. Turning to the app, we can see that when the spectrum data is received, the model number is checked to see if it starts with a Y, which indicates the model uses data encryption. If it does, the serial packet is decoded, then passed to a function responsible for decrypting the spectral data. Interestingly, this function is written in Java, unlike the rest of the app, which uses JavaScript. Decompiling this function reveals that it passes the data to a native library using the Java native interface. This is likely an attempt to make reverse engineering more difficult. With a little help from our friends at the NSA, we can take a peek inside the library. The Java native interface specifies the function name, parameters, and return type, which makes it easy to find and annotate the function. The library also appears to use MATLAB-generated components. MATLAB functions and data types are well documented, which provides useful context for assigning names and types to other variables. This is the most time-consuming step, but it makes it significantly easier to understand the library's behaviour. With some of the variables annotated, it's a good time to work out what we're looking for. A loop will be used to apply the XOR operation, with one key being used for the first half and another for the second. A common optimization is to split a single loop into two separate loops, one handling the first half of the data with the first key and the other processing the second half with the second key. This avoids performing an extra comparison for every iteration. None of the loops in this function match what we're looking for, but there's a call to a function named decodeSpec, which sounds promising. Within decodeSpec, I can immediately see two loops that look like the exact sort of thing we're after. But what's all this other junk? Well, this is a case where the decompiler is making things more complicated than necessary. Switching to the assembly view, we find it corresponds to a couple of SIMD instructions. SIMD, or Single Instruction Multiple Data, is a way to accelerate repetitive operations by processing multiple data points simultaneously. In this case, each loop iteration performs an XOR operation on 16 values at a time. Since the number of data points might not be a multiple of 16, there's another loop to take care of any remaining data. Now that we've identified where the keys are used, we can backtrack to find out how they're calculated. Compilers will often reuse memory for multiple purposes, which can make the resulting code tricky to follow. it seems like a lot is happening before the decode spec function is called, but once again, the assembly view provides a clearer picture. Over 100 lines of C correspond to just a handful of assembly instructions, which are mostly responsible for formatting and reordering data. We're getting close, but there's one final step. The function returns spectral data in floating point format, but after decryption, it's still in integer form. Following the decrypted data, we again find two loops, a SIMD implementation for bulk processing and a standard implementation for any remaining data. Each data point is divided by a scale factor, which is calculated by raising 10 to the power of an exponent. This exponent is encrypted with an XOR operation, but this time, a fixed key is used. Now that we understand how the data is decrypted and scaled, we can write a decoder in Python. This finally allows us to extract spectral data without relying on the supplied software. I've released all the software in this video under the GPL license. You can find a link in the description below. For its price, Torchbearer has managed to deliver an impressive spectrometer. Its compact design and extended infrared coverage set it apart from more expensive alternatives. However, it isn't without drawbacks. The software is frustratingly limited, the protocol is encrypted, and the UV performance doesn't seem to match its specifications. So, is it worth buying? If you're after an affordable spectrometer for basic measurements and can overlook its limitations, then it could be an excellent option. If you've got an Android device and don't mind tinkering with the app, then you can turn it into an extremely powerful tool. But keep in mind, there's no guarantee that the manufacturer won't change their encryption methods in the future, requiring another round of reverse engineering. If you do decide to pick one up, I'd recommend buying it from a place with a good returns policy. I've put links to their store pages in the description below.